So we have already seen an example of cup product for orientable surfaces. So here we will draw a non-orientable surface of genus G. We will denote this by N. Now we have already seen in the case of two-hole torus, which I drew on the previous slide, that the cup product, say alpha 1 cup with alpha 1, is 0. Yeah, so you can take any two simplex and see alpha 1 cup with alpha 1 or phi 1 cup with phi 1, the co-cycles which represent alpha 1. So we said that and it is true for alpha 1 cup, alpha 2 and so on. Here in this case, alpha I cup with alpha I will be 1. So alpha 1 cup with alpha 1 is 1. So it is non-zero. And as I mentioned before, in the case of the torus, two-hole torus, we saw it was 0. So we need to make this thing precise. So first we draw the non-orientable surface. Yeah, so this is genus 2 surface. So as you see, the way the edges are being identified, we have a central point K. Now notice that this is a non-orientable surface, but for each simplex we have a natural orientation. Yeah, so this is the natural orientation. Now this will be important for each simplex. We have an orientation. The surface is non-orientable. Yeah, that is because the way we glue edges together. So now, what is the homology of this non-orientable surface? So we are taking the coefficients in ring Z2 instead of our normal Z. So the homology, this is generated by the edges A1, A2, A3 and A4. So I'm writing AI here. Corresponding cohomology is alpha I. So let us draw this. So this is alpha 1. Similarly, we can draw alpha 2, alpha 3 and so on. So this you can find on page 208 of Hatcher. So we are really interested in finding out the cup product of alpha 1 cup with alpha 1. So ideally I should denote alpha 1 by a co-cycle and then act on this associated simplex. But how I'm going to act on the simplex here, K V0 V1. So let us write alpha 1 cup with alpha 1 acting on K V0 V1. So just shaded it. So notice that the way we write the simplex, yeah, K V0 V1 represents the orientation of that simplex. So again, this entire surface is not orientable, but the smaller simplices which we are cutting together, they have orientation. So why is the orientation lost? The orientation is lost precisely because we are gluing adjacent edges with each other. So concept of orientation will become clear later on when we define orientability properly, but for now just take it on faith. So yeah, so notice again alpha 1 cup with alpha 1 is 1. Now if it was a torus, a two-hole torus, this alpha 1 will not land in adjacent cells. So as a result, whatever cell you might pick up, you take alpha 1 cup with alpha 1 and you take orientation of that cell into account and apply this, you will always get a 0. So, but you notice that alpha 1 cup with alpha 2 or alpha 1 cup with alpha 4 or alpha 3 is 0 precisely because alpha 1 and alpha 3 do not meet. Alpha 1 and alpha 2 do not meet. So they do not even lie in the same simplex. So one of the co-cycle, when it acts on this simplex, will give 0, and 0 times 1 will give you 0. So that is precisely the reason. Now for genus G equals to 1, what we have is a RP2. So let us write down when genus is 1. So what is the corresponding cup product map here? We go from RP2 times RP2. So cohomology of RP2. So alpha 1 cup with alpha 1 is the generator of cohomology H2. So yeah. So you take the cohomology group in H1 and they generate the same, the cup product generates H2. And that is the end of the story.